Laplace's equation in an annulus. This is problem number 3 on page 197 in the textbook. Here we have Laplace's equation in polar coordinates on the domain 0 less than r rho 1 less than r less than rho 2. So it's the region shown in the picture in the upper right. And we have two boundary conditions. On the inner boundary, the solution should take on the value f of theta. And on the outer boundary, the derivative with respect to r should vanish. Also, because the negative x-axis intersects the domain, we're going to necessarily require periodic boundary conditions for the theta variable. The next step is, of course, to separate variables. U of r and theta is r of r times f of theta. Substitute into the differential equation and divide by the product, and we end up with the equation at the bottom of the screen where I've separated them on two sides of the equation. On the left, a function of r alone. On the right, a function of theta alone. And we're led to the conclusion that both sides must be equal to a common constant. So we end up with two equations. In fact, on the left at the bottom here, f double prime plus lambda f is the differential equation, and we have periodic boundary conditions. On the right, the r equation is a Cauchy-Euler equation, and since r equals 0 is not in the domain of this problem, there are no extra conditions. We can solve the f equation because it's a standard equation we've studied multiple times this semester. The eigenvalues and eigenfunctions are shown here at the bottom of the screen. Lambda equals 0 is an eigenvalue, and its eigenfunction we'll take as the number 1. And when lambda sub n equals n squared, n starting at 1, we have the sines and cosines combination for the eigenfunction f sub n. Now that we know the lambdas, we can solve the r equation. When lambda equals 0, we get r squared r double prime plus r prime, and has solution alpha 0 plus beta 0 log of r. When lambda is positive, lambda n equals n squared, we get the Cauchy-Euler equation there, and the general solution is alpha n r to the n plus beta n r to the minus n. We keep both pieces of the solution because r equals 0 is not in the domain. So here I've written out the general solution. U of r and theta will be r0, f0, plus the sum of the product. This is r sub n, and this is f sub n. And I've expanded out the right-hand side here. And notice the products of these coefficients. We've got alphas and betas, a's and n's, but they show up as products. And so I'm going to relabel this. I'm going to call alpha n a n, capital A sub n, beta n a sub n, capital B sub n, and so on, so that the general solution looks like this. It's a lot simpler. Because my handwriting is not so good, I've decided to switch over to Tech, and here I've tabulated the general solution in the first line, where I've redefined the coefficients, and the r partial derivative in the second line. We'll need it for the second boundary condition. So applying the boundary conditions, when we set rho equals 1 in the general solution and require that we get f of theta, leads to equation 23 here. And in fact, we recognize this as a full Fourier series for the function f of theta. The coefficients for cosine and sine are a bit complicated, but nonetheless it's a standard Fourier series. The boundary condition that when we evaluate the function at rho equals 2, the outer boundary, leads to equation number 24. And this is a full Fourier series for the zero function 0. Let's look at the first boundary condition. This is, as I mentioned, a full Fourier series for the function f of theta, and we can use the standard formulas for the coefficients. So a0 over 2 plus beta 0 over 2 log rho 1 is given by 1 over pi times the integral of f of theta, and the coefficient an rho 1 to the n plus bn rho 1 to the minus n is given by the integral of f times cosine n theta, and the cn's and dn's in the last equation are given by the integral of f of theta sine theta. These are standard formulas for Fourier coefficients. Let's next look at the second boundary condition given at the top of the screen. This is, as mentioned earlier, the full Fourier series for the zero function, and that tells us that, in fact, all the coefficients are going to be zero. So the standard coefficients that involve the integral of the left-hand side 0 will give 0, give these three equations for beta 0 and formulas relating a and bn and cn and dn. Let's collect together now the equations to solve for the six different coefficients given here in equations 27 through 32. You notice that they appear in pairs. The first two determine alpha 0 and beta 0. The middle two determine ANs and BNs, and the last two determine the CNs and DNs. These equations can be solved in pairs. Notice these two, right off beta 0 is 0, and hence alpha 0 over 2 is given by the right-hand side. So there's the solution for alpha 0 and beta 0. Similarly, to solve the other two equations, pairs, there are standard Fourier formulas, and I've used Maple to solve for the coefficients, and here are the formula for the ANs and the BNs, and similarly the CNs and DNs. Maple's solve command is quite useful for these a bit more complicated equations.